In the meantime, good afternoon and welcome to the Alpha University Bergren Forum. My name is John D'Angelo and I am a professor of chemistry and the host of the fall 2024 season of the Bergren Forum. This is episode 7. Today is Thursday, October 17th, 2024, and for those of you attending the forum online, here in Western New York, it is a beautiful, sunny, but seasonably chilly day, and inside Nevins Theater of the Powell Campus Center, it is warm and cozy, and the coffee and tea are hot and free. Before starting, we have a few announcements. First, next Thursday's forum will be given by Corey Fechtow, Assistant Dean of the College of Liberal Arts and Sciences. Corey's talk will be titled The Art or the Artist, Where is Anna Mendieta? There are some other events this week to announce. Namely, later today at 4:30 in this very room will be a talk given by Christine Tarkowski, part of the Arts Speaker Series. Christine will be presenting their work and artistic practices. This Saturday from 7 to 9 p.m. in the Herrick Library Book and Lounge will be the first team trivia night of the semester. Come compete for prizes and make sure you come up with a funny team name for my friend and the host, Mike Allen. The Department of Theater will hold open auditions for acting roles in the spring production of Macanal, a play by Sophie Treadwell. Auditions will begin on November 19th. Today's forum will be given by Connor Robinson, AU Physics and Astronomy Assistant Professor, and the title of the talk is Viewing Star and Planet Formation Through the Lens of Accretion. Take it away.
All right, can you hear me? Great. Okay, so today I'm going to be talking a bit about how stars and planets form through accretion, which is this process of moving material from one place to another place, and in this case, moving it from a disk onto a central star or planet. However, before we get to that, we should talk a little bit about stars and planets in general. And one thing to note about these objects is that they're incredibly common. If you go up and you look up at the night sky, and there are beautiful, clear skies that we've been having for the last couple of nights and should have for the next couple days, you might see something that looks a little bit like this, perhaps a little bit less spectacular, where we see many, many stars. In fact, hundreds of millions of stars in our own galaxy, and there are hundreds of millions of galaxies out there too. So stars are incredibly common objects within the universe, and so it'd be good to know where they come from, because they end up dominating a lot of the processes that govern how our universe actually works. Some of the basics of stars are that they are these massive hot spheres of plasma that are converting hydrogen into helium in their cores. And through that process, they release the energy that powers every process that happens on the Earth. There are a range of stars. I'm going to be focusing mostly on the smaller stars today. There are separate formation processes that happen for larger stars. We're just going to be talking more about stars like our own today. Our own star has a temperature of about 6,000 Kelvin. So relatively hot, but it ends up being a somewhat average star in terms of the full spectrum of tiny stars all the way up to these massive stars that are 40,000 Kelvin. The other thing you might notice if you look up on a particular night is you might also see things like planets. And so this is the sky at midnight tonight produced through a free planetarium software called Stellarium that you can download. So if you're ever curious about what's up in the sky, Stellarium is a really great resource. Here we can see two planets. We can see Jupiter and Saturn. Then you might also see the moon. I'm not going to talk too much about moons. They're also forming within all the processes that I'll talk about today, but we're going to skip moons for now. It turns out that planets are also really common. In fact, the Kepler Space Telescope mission found that most stars host at least one planet around them. Some stars host many planets around them. Things like the TRAPPIST system, which you may have heard about in the news, host something like 7 or 8 planets around them that we've detected so far. So planets are also really, really common. Here are two plots demonstrating this. On the left over there, we have the number of planets per star as a function of their radii. This plot, there's been attempts to correct it for the biases that come into play when you're actually looking for exoplanets. And you can see something like, 10% of stars have a planet that's somewhere around 2 times the radius of Earth orbiting it, which is an incredible statistic and something that we didn't know 2 decades ago. So planets are incredibly common in the universe. Over here on the right, we have a similar sort of plot. This is showing our current known exoplanet population, so all of the planets that we've detected. I'd be careful about looking too much into and trying to glean information from this plot. Turns out there are a lot of biases in terms of how we actually detect planets. But the point stands that planets are incredibly common. We know of thousands of them. And so again, it'd be great to know how they actually formed. A couple basics on what planets are. They are defined by 4 characteristics. So it has to be in orbit around a star. You can't have something like a moon orbiting another planet. That would not be a planet. It has to be big enough to be spherical in shape. So things like potato-shaped asteroids that we find quite commonly in our own solar system are not big enough to actually circularize under their own gravity, so they're not planets either. The third one is a little bit more contentious. If you were following the Pluto debate back in the early 2000s, planets need to be big enough to clear out their orbit from its gravity. And so Pluto did not satisfy that criteria. And so Pluto is not a planet. Don't feel too bad for it. It is the king of the dwarf planets in the solar system. It also has a nice little friend that follows it around. So don't feel too bad for Pluto. It had it coming. Number 4 is one that is a little bit less, perhaps a little bit less spoken of, and that it can't have undergone fusion at any point. This one is critical for distinguishing planets between more massive things, where the first 3 are between less massive things. So it not having undergone fusion at any point distinguishes it from things like stars, and potentially even things like brown dwarfs, which are some people called failed stars, which in my opinion is more offensive than considering Pluto not a planet. So, stars are common, planets are common, but how do they form? Well, as in any sort of science, you have to go out and you have to look for evidence, and you put that evidence together to form some sort of coherent story that is backed by all of the factors that you uncover. So let's look at our own solar system first. That seems like a reasonable place to start. We know more about our own solar system than any other solar system in the universe. Before we can do that, though, we need to have a little bit of physics to understand what we're actually looking at in our solar system. And so we need to talk about angular momentum. So angular momentum is this conserved quantity which describes how things spin and how they orbit around things. So the sun is spinning, the Earth is also spinning, and then the Earth is orbiting around the sun. And all 3 of these are examples of objects that have angular momentum, because they're spinning or they're revolving around something. The reason that we talk about angular momentum in the first place is that it's a conserved quantity, which means that you can transfer angular momentum to one place or another, but you can never create angular momentum or destroy it. The net angular momentum always has to be the same. Actually calculating angular momentum, it ends up being proportional to the mass, the velocity, and the distance from the rotational axis that the objects are revolving around. So for example, for the Earth, this distance from the rotational axis would be, if it's spinning, it'll be the Earth's rotational axis, or if it's revolving around the sun, then it's going to be the distance between the Earth and the sun here. Okay, so we now know a little bit about angular momentum. However, there ends up being kind of an interesting centuries-old mystery in our solar system when we look at where the angular momentum is compared to where the mass of our solar system is. So 99% of the mass of our solar system is in the sun, which is at the very center of our solar system. So all of the mass has been concentrated at this one point to very good effect, to very good order. However, if we look at the angular momentum of our system, over 99% of the angular momentum in our system is actually in the planets orbiting around the sun. And so this suggests that there must be some sort of process that happens in the early part of the solar system that separates the mass from the angular momentum in the system. And so this is something that has been hotly debated for hundreds of years about what is causing the separation between mass and angular momentum. And we can actually start to get a little bit of sense of what this process might be by looking at our solar system. And so this is a diagram showing the orbits of the planets and the dwarf planets in our solar system. And you can notice some interesting things. So if we look at our planets, which are the blue ones, all of them are in basically a single plane, and they end up also revolving in the same way. So all of the planets are going this way in concentrically larger orbits. The dwarf planets end up having a little bit of a different distribution. Here is our friend Pluto up there. And along with a couple other dwarf planets that have been discovered recently, Pluto's a planet. The rest of these have to be planets too. So I hope you like counting up to thousands of dwarf planets rather than 10 planets, or 9 planets rather. But you can notice that all of the planets are in this plane, which is an indication of how they actually formed. We can only go so far with studying our own solar system because the formation of it happened a long time ago. However, space is big, and there are other solar systems or other stellar sisters forming at the same time, or right now. And so what we can do is we can go out and we can observe these systems, and this also gives us a clue as to how things might have formed in our own solar system. And so these are the Orion proplids, which are these really, really tiny, dense things that give us these clues as to what may have happened in the early parts of our own solar system. And if you look very, very closely at them, they look like disks, which makes some amount of sense because the objects in our own solar system are also flattened into a single plane, which might have emerged from a disk. And so forming this accretion disk, and accretion refers to the act of concentrating mass onto another object in space. This is a solution to our problem where 99% of the angular momentum in our system is in planets and 99% of the mass is in the sun. Accretion allows us to separate those two quantities. And so basically, you take a disk, and over time, the angular momentum is pushed toward the outer parts of the system, the mass is pushed inward, and over densities in the disk end up forming planets that we know and love today. Okay. So let's go through this whole system in 6 easy steps, or how to build a star in 6 easy steps. So in the very beginning of our solar system, we started with a pre-stellar core. This is basically a slight overdensity in a molecular cloud that begins collapsing over or under its own self-gravity. Over time, our scales that we're looking at are getting smaller. So AU down there are astronomical units, or the average distance between the Earth and the sun. So our cloud begins collapsing. As it begins collapsing, it ends up rotating because the initial cloud also has some angular momentum. As it rotates, it ends up beginning to form a disk here. And at the very center of that cloud, we have an embedded protostar. So a star that hasn't quite started fusing hydrogen yet, but it's on its way to do that. As this process happens, you may also see things like jets that spew material out the poles of the star. And over time, this will continue to, the envelope surrounding that star that was the original molecular cloud will begin to disperse. You might see these jets actually poking through that cloud. The disk becomes more well-pronounced, and we start getting close to the regime where our star can actually start fusing hydrogen into helium. Continuing on, eventually that cloud has fully dissipated to the point where we can actually see down to the surface of the star. So where before we had this cloud blocking our view, that's now dispersed. We can just see down to the star. The disk is still present, which is indicated by these blue lines here. And during this stage, we still have material flowing towards the central star and angular momentum being pulled away from the central star. We also have things like winds being launched off the surface of the star. That can also carry some angular momentum away from the star itself. We'll talk about that towards the end of the talk. But these objects are called T-Tauri stars. Over time, it begins to settle down even more so than it was during the T-Tauri star. A lot of the gas and the dust has now dispersed from the system or been accreted onto planets or the star itself, or thrown off into space through gathering more and more angular momentum. And we arrive at a debris disk. And then finally, once things really settle down, we end up with our planetary system that we know and love today, where we have these planets in these roughly circular orbits going around our star. And also things like comets as well, indicated by that little point over here. By the way, there is a comet that is viewable from Alfred tonight. So if you get a chance, look towards where the sun is just set, and you may be able to see it. It should be easier to see with binoculars, though. However, in this talk, we're going to be focusing on T-Tauri stars, so this intermediate stage in which you can just first see down to the surface of the star itself, because that ends up being really useful for studying the processes that are happening in the inner part of the disk, which is what this talk is going to focus on. Okay, so before we actually get to talking about the results, though, we need to talk about how we study the universe. And it ends up being quite convenient that we're in Alfred, because our motto is fiat lux, which means let there be light. And this is how we study the universe. Of course, this is not conforming to brand standards, so that's a little bit better. But in general, we're going to be using light to study the universe. And in particular, we're going to be looking at different colors of light through the electromagnetic spectrum. So the electromagnetic spectrum describes wavelengths of light at their shortest, most energetic end in the form of things like gamma rays and X-rays, all the way to the least energetic forms of light in forms of things like radio emission or radio waves and microwaves. The majority of this talk is going to be focusing on light that is sort of in the middle of these two, of either the ultraviolet light, a little bit in the infrared, and then the visible light that we can actually see with our eyes. But light is the primary messenger that we use in astronomy to learn about how stars work and how all of the processes that govern how they evolve over time. One of the tools that we use to study light is spectroscopy, which is splitting light into its constituent wavelengths and then measuring how much light we're getting at every color or every wavelength. And so this ends up encoding a ton of information about the object that we're studying. So this is a spectrum of our own sun. And you can see all sorts of interesting patterns and lines here. There's some overall shape, which ends up telling us something as well. This is looking at light going from the ultraviolet, so shorter than about 400 nanometers is ultraviolet. This would be our optical regime, as indicated by the colors. And then beyond about 700 or I guess about 800 nanometers, you go into the infrared. And so all of this information is encoded within the spectrum of the star. And it turns out that this is one of the primary ways that we learn about the universe is through this tool of spectroscopy. So let's learn a little bit about what this spectrum is actually telling us before we get to our young objects. So the first thing that we can study with spectra is the overall shape of the spectrum. And this ends up being controlled by something called by Planck's law, which basically describes how much light you're getting from an object if that object is emitting because it's hot. So objects in the universe emit light, and hotter objects in the universe tend to emit more light, and that light tends to be bluer light than cooler objects. And you have some sense of this by if you turn on your stove begins glowing red, and if you really turn on your stove, it begins glowing, a little bit oranger and yellower. And if you really turn on your stove, it turns hot white, and then your stove catches fire and your house burns down. So don't do that, but that's what happens if you really turn your stove up. So avoid doing that. But the general trend happens for stars as well. The hotter they are, the brighter they are, and the bluer they are as well. And we can see this through this diagram, where I've plotted the Planck function for a couple different temperatures. So something like a 3000 Kelvin star, 4000, 5000, and 6000. So this would be pretty close to what the actual sun looks like. And you can see that the majority of the emission from the sun is going to be in the visual light that we can see with our eyes. The other part of the spectrum were those dark lines where it seemed like a little bit of light had been chunked out of it. And these relate to the composition of the object. So atoms and molecules can absorb energy in the form of photons or of light at very specific wavelengths. And that ends up changing the spectrum that we see depending on the temperature structure of the object that we're looking at. So over here, I have a little diagram. The light bulb is basically representing a thermal emitter, so something that is emitting like the Planck function. And so if we go out through and we observe that object through a prism, it's just going to give us a rainbow that we see on the top there, a continuum spectrum. If instead we say, I don't know, heat up a gas in a tube and then observe the emission that's coming from that hot gas of a single particular element, we disperse it, we're going to get something that looks like the middle there. We have an emission spectrum where we have these lines, again, from the absorption or the emission of by atoms at very, very specific wavelengths of light. And so we end up with this discrete emission line spectrum. The locations of these lines in wavelength space, or the color of these lines of these lines, tells us about what the object is made of, because this is a unique fingerprint that corresponds to that particular atom or that particular molecule that's doing that absorption or emission. And then if we combine these two and we have a hot object behind a cooler cloud of gas, we're going to end up with an absorption line spectrum where we have a continuous spectrum with these dark lines superimposed on it that are basically indicating the presence of those atoms in the upper layers of whatever object that we're looking at. Finally, I don't have a diagram for this one, but it's one that actually pops up in my research quite a bit. If we have a hot object like a star with even hotter gas in front of it, you get the continuum spectrum, and then you actually have bright lines where those emission or the absorption lines would be instead. So you get basically the reverse of your absorption line spectrum at the bottom there. So this corresponds to a geometry where you have something like a hot star, and then we have even hotter gas in between you and the star, and so it tends to glow that way. But the implication for this is that we can use these spectra to explore the universe. We can tell what something is made of and the temperature structure of that object just by dispersing its light into its constituent wavelengths. This is an incredibly powerful technique for learning about the universe. So now we can put it all together. From the peak of this curve, we can measure the temperature of the sun. From the lines, we can measure the composition of the sun. We can measure the structure of the atmosphere of the sun. There's so much information encoded in a single spectrum of just the sun. It's incredible. And to toot our own horn a little bit, we just recently added a spectrograph to the observatory. It's something that we're working on commissioning, and we're just starting to gather data using this instrument, which is really exciting. So look forward to years of research using that instrument. Okay. So let's apply it to our disk system, returning to planetary and stellar formation. So here's a diagram of what a protoplanetary disk and a T-Tauri star look like, where we have our young star in the center, surrounded by this protoplanetary disk. And then within that disk, we have things like protoplanets beginning to form potentially. We also have distributions of dust grains and things that you can study, primarily at longer radio wavelengths. But in general, the temperature of the object is going to define how we can actually go about observing it. And this is because of that Planck function peaking at either longer wavelengths for cooler objects or shorter wavelengths for hotter objects. So you can think about the distance from the star is going to be a proxy for how hot that disk is. And so that's going to tell you basically where in the spectrum it's going to be emitting the majority of its light. And so up in the upper left corner there is a spectral energy distribution. You can think of this as a spectrum, but over a very wide wavelength space. So this is going all the way from the ultraviolet all the way to the radio emission, all shown in one plot for a particular object. The light blue dashed curve there is the emission coming from the protoplanetary disk, primarily emitting in millimeter and radio wavelengths. The dashed magenta line there is radiation coming from that's being reprocessed by the inner edge of the disk here. And we can see that's mostly in the infrared. And then the star itself is also emitting the majority of its radiation, which is the yellow dashed curve there in the optical, just like our own sun. And so by combining these multiple components, we can do a pretty good job of recreating the observed data, which are all of the teal points and the yellow spectrum there. However, there's a piece that's missing from this. If we look at the very short end of our wavelength space, there's a little bit of excess flux, and that is from accretion. So there's extra light generated from material that is transferred from the inner edge of the disk onto the star. And so let's look into how this process actually occurs. So we're going to come up with a simple model of accretion called spherical Bondi accretion. So basically, we're going to work under the assumptions that you have some amount of gas and dust that is around the central star, and it's just going to be falling toward the central star. You can describe this system using the fluid equations, which are essentially, at least the ones that we're using here, they're essentially just conservation laws. So similar to angular momentum, we can also conserve linear momentum and mass. And so if you make a bunch of assumptions, and the ones that I've made here, your fluid equations end up looking like this, where you have some calculus over there, and then this is basically just a statement that the total mass of the system is conserved, and then some more math over there, and this says that the linear momentum of the system is conserved. You can then go through and you can solve these equations. It ends up being something you can actually solve analytically, which is fun. And you end up with this result, where this is a plot of density on this axis, and then distance from the star on this axis, and then velocity on this axis. So what we find is that the material, as it falls towards the surface of the star, smoothly passes through the point where it becomes supersonic. So you have this supersonic material falling towards the star at something around speeds of 300 kilometers per second. 300 kilometers per second, which is ridiculously fast. And so that suggests that something energetic is going to happen when it strikes the surface of the star. Somewhat oddly, this is how rocket engines work, or so the math ends up being very similar to how rocket engines work, where gravity and the actual spherical geometry of our material converging to a single point end up playing the roles of adjusting the effective area of our nozzle in some sense. So just kind of an interesting analog between those two things. Okay, so we have material falling towards the star really, really rapidly. However, this is not quite what happens in young stars, and there's some additional physics that we need to fold into our models. In particular, charged particles tend to spiral along magnetic field lines. And in the environment where you have a hot star, you're able to remove some of the electrons from their atoms, and they end up spiraling along these magnetic field lines. And so you get something that looks something like this. This is interesting to consider for individual particles, and there are whole branches of physics that deal with this problem. But if you scale this problem up into something like the size of a star, and you consider lots and lots of particles all spiraling around their magnetic field lines, you get something kind of dramatic that you can actually see when you look at pictures of things like the sun. So this is an X-ray image of the sun, and you can see all of this beautiful structure that's caused by essentially particles spiraling around magnetic field lines. So for example, here we have a magnetic field line that connects from this patch of the sun over to here, and you can follow along it, and you can see all of those particles that are suspended above the surface of the sun. And so this is effect of particles, being guided along the magnetic field lines of the stars is also something that we need to consider for our young stars as well. However, this is a picture of the sun when it's 4.57 billion years old. And so this sort of raises the problem of, or at least the question of, what did the magnetic field of the sun look like when it was very young? Does it look the same as this? And the answer is no, it actually looks a little bit different. And it turns out that magnetic field lines of young stars end up looking surprisingly simple. They look somewhat like bar magnets, in which you have a north magnetic pole where you have the field lines coming out. And so you could have material suspended along those magnetic field lines or following along those magnetic field lines. And this ends up guiding the material that is from the disk as it falls to the star, rather than just falling directly onto the star itself. For comparison, for how strong magnetic fields are around sort of typical objects, something like a fridge magnet has a magnetic field of about 100 Gauss. The strongest active regions on the sun are something like 200 Gauss, so those were maybe where we were seeing those magnetic field lines connecting into the star before. The quiescent sun, or the rest of the sun, is something about 1 Gauss. For comparison, young stars have magnetic field lines of something like 4,000 Gauss, which means they have much, much stronger fields, which means that their magnetic fields can influence the surrounding region to a much larger radius. And so this is actually a pretty incredible figure here. This is a map of the magnetic field structure of a T-Tauri star. The way that you obtain this is pretty complicated. It involves spectra. So we're not going to talk too much about that, but it is a map of basically the strength of the magnetic field around another star. And what we're looking at here, this cross here, is the pole, the magnetic pole of the, or sorry, the rotational pole of the star. And then the dark red spot here is the concentration of these field lines, basically from the upper end, the northern end of the bar magnet over here. And again, it ends up being a pretty good approximation for what young stars look like. Okay. So we have this material being guided along magnetic field lines. It's falling towards the surface of the star. It's falling at speeds of something like 300 kilometers per second, which means it's going to smack into the surface of the star. As it smacks into the surface of the star, all of that kinetic energy is released in the form of X-rays. in this post-shock region. So here we have our material falling down, hitting the surface of the star, shocking, and that creates these X-rays that are generated in this region. Those X-rays flow upward into the pre-shock region, which ends up heating as well, and towards the surface of the star. So you end up having a little hot spot on the surface of the star. This whole area is opaque to X-rays. They don't actually escape the system. They're all absorbed, at least for the most part, by the accretion column. But this energy has to go somewhere, and it ends up being reprocessed into ultraviolet radiation that we can go out and observe. So over here is an observation from the Hubble Space Telescope of a T-Tauri star called BP Tau. Here are the observations in black. So this is an emission line spectrum where you have some continuum emission and then these narrow lines, primarily coming from hydrogen in this case. And we can model this and break it into some constituent parts. So here is what the star would look like if it didn't have any accretion going on. And then here is the emission coming from the heated photosphere, so that part at the bottom. And then this emission in the ultraviolet is coming from the pre-shock, so that region right before the material slams into the surface of the star. And if we add up all of these components, we can do a pretty good job of modeling what the observations actually look like. And by doing so, we can learn about the conditions that are right near the surface of the star, where this material is colliding with the star. Okay, so let's put this all together to form our current schematic of what young accreting stars look like. So we have this dusty disk that extends for a couple hundred times the distance between us and the sun. That ends up being truncated by this very strong magnetic field, which can disrupt the inner disk. As that material is disrupted, it flows along the magnetic field lines, reaching speeds of a couple hundred kilometers per second. That smacks into the surface of the star. That heats up a little patch on the surface of the star. And we can study that by looking in the ultraviolet because that's where that emission or that kinetic energy has been reprocessed. This also fits into our picture where we had this excess emission coming over here, and we have a nice coherent picture of what stars look like. In terms of how much material is actually smacking into the surface of the star, typical mass accretion rates are something like 10 to the -8 solar masses per year. So if you think about the sort of typical lifetime of a T-Tauri star is about 10 to the 7th years, you end up accreting about 1/10 of a solar mass over its lifetime, which is a fairly reasonable amount given that stars weigh about, or at least our star weighs 1 solar mass. For a little bit of nomenclature, young low mass accreting stars are known as classical T-Tauri stars. So if you hear me refer to them as that during this talk, that's what I'm referring to. Okay, so let's actually look at one of these objects in a little bit more detail. So this is G Auriga. It ends up being an excellent candidate for studying accretion onto T-Tauri stars, in part because it's a young solar analog, so it looks very much like our own sun did at the beginning of its life. And it is robustly accreting pretty typical, something, again, around that 10 to the -8 solar masses per year. The thing that is really nice about this system is that it is moderately inclined. So you think about it, it has a disk. And if we were looking at the disk edge on, we'd be looking through all the material in the disk. But in this case, it's slightly inclined. And so we're seeing it like this. So we're able to see down into the central star. And so over here, this is an actual image of G Auriga, or at least the disk around G Auriga. This is a radio observation, and this is how we are measuring basically that inclination of the disk, because we can actually just see it, which is pretty neat. Disks end up being really complicated objects on their own. There's all sorts of interesting substructures and things that happen in disk that may be evidence of planet formation, but that is a whole different talk. So, zooming back towards the central star, and we have our material being guided along the magnetic fields towards the central star itself at very high velocities. And as this material is coming in, it turns out that the density of the material is going to be proportional to the amount of energy that's released as it slams into the surface of the star. And if you have more energy being released, that means it's going to heat the surrounding areas to be hotter, and that means that the emission is going to be bluer. And this is something we actually observe as well. So on the left over there are 3 models of this accretion process, where we have a high density accretion column, a medium density accretion column, and a low density accretion column. And you can see that the low one has been shifted to longer wavelengths, which means less energetic light, or redder light. If we go out and we observe one of these objects, we can decompose the observed spectrum into the amount of energy or the amount of light that's being released by different contributions from these accretion columns. So we can say how much of the star is covered by these high density columns versus these low density columns. And so this allows us to distinguish between sort of two different scenarios of all of the material being accreted with a single column density, between something like this where we have the accreted material being contributed by columns with different densities. And so the first result that I'd like to share is looking at this process of this decomposition for Gamma Auriga, which is again this accreting young star. So just like the previous figure, the data is in black, the total model is in red, and then we'll go through each component here. So the data itself comes from the Hubble Space Telescope, in particular the Space Telescope Imaging Spectrograph, which is just a spectrograph on HST. The blue component here is a non-accreting star, so what the star would look like if there was no accretion happening onto it. The lines down here are different column or different accretion column densities. So the blue ones are low density, green are high density or medium density, and pink are high density columns. And then the numbers down there are the actual fraction that is covered by the fraction of the stellar surface that's covered by these accretion chunks. So something like 9% of the star is covered by these low density accretion columns. And then you add all of those model components up and you end up with the red line, which does a pretty good job of reproducing our observations. If we can look at the total fraction of the mass accreted by each column, we end up with this nice little pie chart here, showing that a little over half of the material that's falling onto the star is in the form of these low density accretion columns. And then the other roughly half is the medium and the high density columns. And so this gives us a way to basically look at the inner regions of the star, or the inner regions of the star disk system, which is too small, at least with as far away as it is, it's too small to observe using almost all techniques. There's a couple measurements. We'll not talk about this. But this lets us basically study the inner regions of the disk. And so what we can do with this is kind of fun. So that was a single measurement that I showed before. This was part of a larger monitoring campaign of Gamma Auriga, where we went out and we observed this object multiple times using the Hubble Space Telescope. Because as time progresses, the star is going to be rotating, and the accretion hotspots are also going to be rotating. And so the amount of material that we're able to see along our line of sight is going to be changing. And the accretion rate itself can also change, and maybe the distribution of columns across the surface of the star can also change. And so we went out and we monitored this object, and we found, just like we did before, that the majority of the star, at least the largest fraction, is covered by these low density components. But there are some amounts of small dense packets or small dense areas in the star that are from these really, really high density parts of the accretion column. And so down here, I'm showing the breakdown of how much mass is being accreted by each component. So you can see in this epoch, we had a very, very little amount from those high density columns, whereas in this epoch, almost half of it is coming from those high density columns, and so on. However, we noticed something kind of interesting when we were looking at our data, in that the peak of the mass accretion rate, which is the sum of all of these columns, is not aligned with when the star was the brightest, at least at longer wavelengths. However, the peak of the low density accretion columns is well aligned with that peak that we see up there, again at longer wavelengths, which is tracing cooler material. And so this suggests that the location at which the material is being accreted has some sort of structure within it. And basically what you're seeing is what is shown in the simulation that went along with this paper, where you have this sort of banana-shaped spot here. Some parts of it are going to be denser, and as those really dense parts rotate out of view, you can no longer see those areas that would light up in the ultraviolet. And you're left with this emission that is more in the optical. And so this was the first sort of, at least, evidence that was shown that these spots do have some sort of striated, or at least stratified density structure across the surface of the spot. We can see that as they rotate, which is a fun little result. The odd shape of these spots we think might be caused by more complex elements of the magnetic field. So it's not just a perfect dipole, but we have higher order components that could make it a little bit more complicated. Another thing that we see with accretion is accretion lines. So as I mentioned before, we can have these really, really bright, or we can have bright emission lines because of hot gas that we're observing in front of something that's cooler. One such example of this are carbon-4 lines. So carbon-4 refers to carbon that has been triply ionized. So you have a lot of energy that goes into removing electrons from these carbon atoms, and they emit in the far ultraviolet. And so these are two lines that come from carbon-4. And you can see they have sort of interesting structures in which you have this narrow component at the sort of center of the line, and then this broader component out here. All of this emission is coming from carbon-4. And so this is a very interesting line shape. There's also a molecular hydrogen line happening over there that is unrelated to at least this particular process. So don't worry about what that little bump is on the other side there. The way to read these spectra is that these are going to be, again, towards longer wavelengths over here, and then shorter wavelengths over here, so redder light and bluer light over here. And I have it written in kind of an interesting way of velocity space, because it turns out that the shape of lines, or at least the wavelengths of lines, can tell you something about the velocity structure of an object as well. And so the way you can think about this is through the Doppler effect. So if you've ever been on the side of a road and you've heard an ambulance go by, as the ambulance is approaching, you hear a higher frequency, and then it zips by you, and you hear a lower frequency as it goes off into the distance. And this ends up being something that also happens to light, because light is a wave. And unfortunately, my video is not going to work, but the same idea applies that if you have something approaching you, you're going to have higher frequency light, and so that's going to be bluer light. And if you have something moving away from you, you're going to have longer frequency light, and so this is going to be redder light. And that ends up being a way that we can basically describe, or we can learn about, the kinematics of objects as they're moving around in space. So this is a little bit of an overwhelming figure, or a slide, but I will guide you all through it. So by taking the observed spectrum of the line, which is shown down there in velocity space, we can model how this line is emitted, and that ends up telling us what the structure of the accretion shock is. And so that is this plot in the middle, which is describing lots and lots of different physical conditions that are happening within this accretion shock. So the top panel here is the density of the accretion shock. So in the pre-shock region, it's a little bit lower density. Then you slam into the surface of the star, the flow slows down, and it becomes more and more dense as you get to the surface of the star. So over to the left is the surface of the star. To the right is away from the star. We can also model the temperature. So we see something like 20,000 Kelvin in the pre-shock region. And then as soon as it slams into the star, we jump all the way up to about 1,000,000 Kelvin, which is what is generating those X-rays that are heating up the surface of the star in the pre-shock region. We can also model the velocity of the flow. So coming in here, hitting the shock, immediately slows down. You can also look at things like the ionization fraction of elements within the shock. So how many of those electrons have been ripped off carbon atoms in the shock? And so that's shown in the next panel. We can look at the excitation, basically how many of those carbon atoms are in excited states versus not excited states. And so all of this lets us really probe the details over what was happening in these accretion shocks over time, which is really exciting. The sort of main results that came out of this work is that the narrow line, the core of the line, comes from the base of the post-shock region over there. And then the broader component comes from the emission in the pre-shock region. So basically you have these X-rays excitating the bottom of this pre-shock, and that ends up allowing you to form carbon-4, which can emit in these waves. The other sort of exciting thing that we learned is that carbon is actually depleted in these accretion flows compared to what we would expect for a normal star. And so this suggests that a lot of the carbon that would be in the material that we would expect to be falling under the star instead is now residing in dust grains within the disk, which makes some amount of sense because we have to have solid materials to actually form things like the planet that we're standing on here. So all of this forms a sort of nice coherent narrative of what's happening within these systems. It turns out that stars are not the only thing that accrete material. Planets also accrete material during their formation process. And so this is an actual image of a planetary system as it is forming and as it is accreting material. You're not seeing double here. There really are two stars that are in the center of that. So we have two stars that are orbiting each other. And then we have a planet that is quite a ways away out there that is glowing because it's hot, because it's accreting material onto it as well. And so this is kind of a unique system where it ends up actually being far enough away from its host stars that it's bright enough and distant enough that we can actually study the planet directly. And we can actually take spectra of the planet as well and learn all about the planets and the processes that are happening there. So on the top here, this is the spectrum of the planet. We have all sorts of emission lines that are related to how much material the planet is accreting. We don't see those emission lines in the star, which means we're actually looking at just the planet alone. This is something that we've done in the ultraviolet, that we have not done in the ultraviolet, but we've done in the optical and the infrared. But I have a program that I'm leading to go out and actually observe this planet in ultraviolet to learn about its processes. And basically, accretion onto planets is related to their formation mechanisms. And the more material that they're accreting, they're accreting more material than we would normally expect based on their mass. And so that ends up telling us something about how we think that they're forming, which is kind of exciting. So this HST program that I'm leading will hopefully answer some questions about how planets form and what formation mechanisms they follow. And then finally, accretion is a really variable process as well. Something like 95% of the objects that we're studying using accretion are varying in some way that we can detect. A lot of this is due to changes in the accretion rate. Some of it's due to rotation of those hotspots on the surface of the star. And I'm part of a NASA mission that is going to, that we're proposing to put up a new space telescope that would measure the brightness of these objects in ultraviolet light and visual light at the same time. And that would help us answer our final question down here, which is to determine whether stars' rotation is regulated by the ejection of material from their inner accretion disks, influencing where planets are born and migrate. So that's a whole mouthful. So we'll zoom ahead to here. This is basically what we're looking at here. What we're trying to answer is where the magnetic field line truncates the inner part of the disk, because that ends up controlling how angular momentum can be transferred to and from the star. It also influences where planets can form and migrate within the disks. The planets also move around within the disk. And so this space telescope mission would help us answer this question by using results from a simulation that I put together over the past year or so. So hopefully we will get that accepted. It's made it through the first gate review. We have another gate review actually tomorrow, which is exciting. So we'll see how that goes. But with that, I will conclude with spectroscopy is really, really powerful. It can tell us about accretion, which is also really powerful for telling us about how young planets form and how stars form as well. And I'm really excited to continue doing my research with our new spectrograph at the observatory for years to come, and other things like the Hubble Space Telescope for years to come too. Thanks.
We are up against the 1:20 hour. It's like 1:10. So if people have to leave because of classes, we won't hold it against you. But if there are any questions, I'll bring around the microphone.
Hey, so this is a psychologist answering a question, or asking a question, sorry. When you showed us a picture of our solar system, it's obvious that there's different spacing between the planets and the star.
Mhm.
Can you briefly explain in words I can understand what governs the, I guess, spacing between the planets? So as it's collecting its carbon dust, are there specific laws or specifics that says, you know, this is how far apart they have to be? And then why in our solar system are they different?
Yeah, so that is a complicated question. I think the first part is that they almost assuredly did not form in the locations that they were today. So they have migrated over time. What's governing that migration is going to be gravitational interactions between objects within the solar system. So if you have one planet orbiting this way and you have another planet going around at the same time, those are exerting gravitational forces on them as well. There are some areas that end up being more stable or unstable, depending on the orbital resonances between them. So if this one goes around 3 times, this one goes around twice, they end up being lined up with each other more often than not, and that can actually tug planets out of their initial orbits, and that can throw them off into, that might even remove it from the system entirely if you have a really strong resonance there.
Any other questions? If not, please join me in thanking Connor again.